So I hope the first part, or maybe the 2/3, is going to be accessible, should be accessible. I did the slides, my intention was to make it accessible to people not working in dynamics, maybe in a broad sense. But if it's not, now we have a keyboard, so I can always explain if something goes too fast. So you can stop me and I'll try to explain the notions properly. Yeah, so it's about chaos in deterministic system. This is a topic I think that became popular in the second half of the 20th century in dynamics. And I will try to explain what I mean by deterministic systems, and I will try to explain what I mean by chaos. And I think chaos in so-called random systems was understood for a long time, and I think the motivation already comes from the Bernoulli process studied by Bernoulli in the 17th century. So here, what you do is you take random variables on some measure space, and the probabilities are that xi equals 0 and xi equals 1 are 1/2, and the random variables are IID. And this models a sequence of independent, in this case, symmetric coin tosses. So what you do is you toss a symmetric coin. Symmetric means that the probability of seeing 0 and 1 are the same, and you perform it many times, and this is somehow, mathematically, this IID models this kind of experiment. You can talk more generally about asymmetric coins, so it's more likely to see heads than tails, and also it can take more values, finitely or later on even infinitely many values, but maybe classically it can take any finite number of values with any probabilities you assign to them. And then, for example, right, if the probability is 1/2, 1/2, 1/2, and you do your experiment like 1,000 times, then you expect 500 times to see heads and 500 times to see tails. How does dynamical systems enter this? Well, so you take the space of, so this is what I would call a not a deterministic system, rather a probabilistic system, and you'll see in a moment why. And now these are called Bernoulli shifts. So you take all possible outcomes. Imagine you have infinite time in the past and infinite time in the future. And in this case, all possible outcomes of your experiment are your phase space. And the measure that you have on your phase space corresponds to the probabilities you started with. So if you have more values for different, if you have more possible states and different values, you have to modify the phase space, but it's kind of natural. And then you have the notion of the shift of this space. So this is a probability space. And you have the notion of the shift, which one important property from dynamical point of view is that it preserves this measure. So if I take an event A, say seeing the heads on step 2 and tails on step 5, and I shift it, my chance of seeing this is the same as, so 3 and 6 is the same as 2 and 5. And more generally, you can model, as I said, any finite alphabet. Here you put 0, 1 to the d, and then you can do any probability vector. So this is a dynamical system. Dynamical system abstract. The dynamical system would be a space with with a measure, usually probability measure, and a transformation that preserves this measure. So this is somehow classically what dynamical systems, how dynamical systems are defined. I wouldn't call this system deterministic, especially maybe there is no one clear definition of deterministic. But you'll see later what type of systems people generally agree on are deterministic. This is rather a random system. First of all, the space. So for a system to be deterministic, I think the phase space usually wanted to be a manifold, and then the dynamics maybe should be given by a solution of a certain set of differential equations, or like by an algebraic formula, which here maybe the shift operator is not that bad, but the phase space is a counter set. And what is the relation? How you can study the coin tosses using this dynamical system? You take random variables defined on this space by the formula which so your function f0 is just the zeroth coordinate of omega. So any vector omega is just an infinite sequence of 0 and 1s, and the function is f0 of omega is omega 0, and then the random variables xi are just the shifted omega. So you compose f with sigma I, and because the way the measure is defined, this function with, this process is first of all stationary, but it's an IID process. And then the left-hand side tells you an outcome of a sequence of 10 coin tosses, and you can interpret it as an ergodic sum for sigma. Okay, so somehow the model for chaos is this system. Okay, so maybe the questions that people started asking, I think late 50s maybe, or mid 50s, was, here I'm not going to be precise at this moment, is to what extent can a smooth system, or like a natural physical system, resemble this system that happens on a strange space. And now now where we are heading to is, I'm going to define some notions that this system has, and then that you want to observe, maybe you want to ask, okay, is it possible in a smooth or physical system? So chaos, that's the first word in the talk, is in vague terms roughly whatever ergodic or dynamical or statistical you can observe here. That's somehow the notion of chaos. And then deterministic systems is going to be some nice, we'll see them later, they'll come. Okay, but hopefully the saying is clear. Yeah, and now I'll tell you what this system satisfies, but I'll state it in terms of an abstract measure preserving system. So Tx mu is, we have a probability space and the map of it that preserves measure. Okay, this is always going to be the setting. For now it's an abstract, there is no smooth, no deterministic yet. In particular, you can put this system, you can put this system inside it. Some notions of chaos, or some notions that describe, complexity of the system. So the main one, I think the basic one is ergodicity, which just tells you that the system can be decomposed into two non-trivial parts, or finite, or any number of non-trivial parts, meaning that if I have a part that's non-trivial in my system, if I have a part that's invariant, so the dynamics somehow inside the part and the complement don't see each other, then it needs to be measure zero. So it's trivial from the point of view of measure theory. And then two more notions, mixing and two mixing. So this is the notion of independence. If I start with a certain event, and then I let it, I take two events, and I let one of them evolve, they should become asymptotically independent. That's two mixing. And L mixing, for any natural number, you can generalize this. It's just I take L events, A0 to AL minus 1, and then I want them to become asymptotically independent as the minimum goes, as the gaps need to go to infinity between any two pushes, any two observables. One simple exercise that maybe you've seen, two mixing implies ergodicity. So if I have two mixing, then I will be ergodic. Okay. But now, so these are abstract definitions. Let's see the Bernoulli shift that we've just seen on the last slide. If I take any cylinders, so cylinders means I fix what happens on. So for an example of a cylinder set would be on my third toss I see a 0. And on the fifth, I see a 1, for example. That's an example of a cylinder set. So when you perform your experiment, the cylinder is fixing certain positions, finitely many positions, and assigning 0, 1, or generally any sequence from the alphabet to them. And it's very easy to see that, you know, in the Bernoulli shift, which is the coin toss, you know, if I'm fixing positions 3 and 5, and for the other one I'm fixing positions 2 and 7, for example, and I move one of them sufficiently far apart, they not only become asymptotically independent, but they actually, as long as n is larger, say, than the size, I mean the positions I fix, it's actually equality, right? So seeing seeing heads on day 3 or third toss doesn't tell me anything about seeing whether I see 0 or 5, 0 or 1 on the 5. And this means that they are mixing, and hence L mixing for any L, because you can do it for any cylinders, and therefore in particular ergodic. Notice that this somehow, I mean, this is quite a trivial observation for the coin toss, but since now we know that Bernoulli shifts are mixing, you can use Birkhoff ergodic theorem. So, you know, in particular, the shift is ergodic, which means that with probability 1, you will see heads roughly 1/2 of the time. Okay, and if the coin is symmetric. Okay, so I mean, this is an overkill. You don't need this theorem just to tell you how it works. Okay, now I will try to. When I did the slides, I tried to be ambitious, and I decided to see the definition, quick definition of entropy. Usually you spend quite some time, but I think the definition that we'll have here is going to be accessible. I mean, it's not the one you usually see in textbooks, but it is equivalent, and I think maybe simpler to digest at least, I hope. Okay, so let's say you have a measure preserving system. Entropy is the crucial thing that measures chaos. So, you know, it's just going to be one slide, this slide in which we are going to define entropy. So first you start with the entropy of partition, and here I think I'm going to use the board. So say you have your space X, and I'll just draw a partition, so P1, P2, and P3. And then given an integer, in fact, or a natural number n, you can code, and you take any point, and you can define the name of the point, which is just you take a point x, and then see where it jumps. So if this is x, tx, say t2x, t3x, the name would be 1, 3, 2, right? Because it's 1, then I'm here, then I'm here, then I'm here. So to every point, you know, I just look where the orbit goes, and I can associate a name. This when I fix the integer. So these are finite codes of n letters, right? And then you can measure the distance between codes. So you have a metric given this n on your space. You can measure the distance between points, which means, you know, I take my point x, it has a certain code. I take my point x prime, it has a possibly different, or usually a different code, and I can count actually how different they are. So I'm looking at, you know, the positions that they agree or they disagree, and I define this. So for example, if they agree everywhere, the number I subtract there is 1, and therefore, you know, they are the same. It's not a true metric, but it's good enough to define entropy. And then what you do is, that's the main, I think that's the main part of defining entropy, and after that everything is easy, more or less. I mean, just the definition. So what you do is, okay, you have your metric on the space that depends on n, and I give you an epsilon, and then you ask how many different codes do I see in my space, okay? And the measure, so, you know, I have a measure space, the measure enters just here. So all the definitions don't see a measure so far. The measure just appears, you know, so I don't want to cover the whole space. I want to cover 1 minus epsilon proportional space. So each point comes with a certain ball, right? This is called the ball and ball, or Hamming ball. Maybe for partitions it's Hamming ball. And then I want to cover my whole space, well, not whole space, 1 minus epsilon space, by these balls in the most efficient way. And
sorry, where? Where are the balls? Any balls?
Yeah, so I have a metric. It's not, let's call it a metric. I don't want to.
That's fine.
I have a metric, so then I have the notion of ball. And then I want to cover my space with the balls in this metric in the most efficient way.
So independent, this has nothing to do with the sequence of points anymore. Now it's just, you just want to find an almost cover of the...
Correct, but the metric has very much to do with this, right? The way I define the metric is, it is a dynamical metric. So I think Bowen was maybe, it's usually called, in a topological setting, it's called Bowen metric. So, like if I have an isometry, think of having, just isometry of your space, then if I start with 2 points nearby, they most likely see the same code up to, right? On the other hand, if I have something expanding, this is where I'm going to probably see entropy. So, okay, does this make sense? So, this number, it is a finite number, say by compactness. Here it's just 1 minus epsilon, so it's just the measure is regular. And then entropy measures, there's this long formula, but the way to think about it is you ask how this grows. So does it grow linearly with n? Does it grow quadratically with n? Most often it grows exponentially with n. So what you do is you take a log, right? If it grows exponentially, you take log, you get a number, you divide by n, and you get the entropy. Okay? So this formula I don't think is, that's how you define entropy, but what is important is you see how many different points you have. And heuristics here is that positive entropy should force you to see exponentially many balls, which means that it's very likely that 2 different points will see different codes. So, even though points will start very close, maybe that's another way of seeing entropy. I will take points that are E minus delta n close, and x is prime, and still their codes are going to be significantly different. Okay, so, and we say that E has positive entropy if there exists a partition with this property. And just to tell you, if I have a Bernoulli shift, so, here I'm allowing all symbols of 0 and 1s, all blocks of 0 and 1s, and I take a number n, right, it is easy to see that I have 2 to the n blocks, because I have n positions, and on each of them I can put either 0 or 1, right, so I have 2 to the n possibilities, 2 to the n different codings, and therefore if you do 2 to the n, you need to work a bit, because 2 to the n covers the whole space, but you show you don't do much better, like with this 1 minus epsilon, and then you take the log, you get n log 2, you divide by n, you get log 2. So that's with this definition, that's how you show that the entropy of Bernoulli shift is log 2, and maybe this is, reversing the way to say that Bernoulli shifts are chaotic. So whenever you see entropy, you should see some chaoticity in the system, some exponential separation. Okay, the next property is very similar to entropy. It's just that Kolmogorov, I think, realized that entropy is maybe not fully the right notion. It is a central notion, but it doesn't capture the whole dynamics in the sense that, for example, you would take a dynamical system that is just identity times whatever, times the Bernoulli shift, say. And in this case, right, if we just take a direct product, for example, on the product space, this part doesn't see any chaos, whereas this part does. The entropy is positive, and there is a very rigid part in your system, right? So he said that the system satisfies K property if for every partition the entropy is positive, right? So the difference is here. Here there exists one. Here we want it for every. And for example, here I think if you took the partition, sets like this, cylinders like this, you wouldn't see entropy. So if you take entropy that sees the Bernoulli shift, it will be positive. But if you take the entropy that only sees identity, by the way, for identity, all the codes are just, right, every point stays put. So the code is just going to be whatever atom it started with. So the number of codes is just the number of atoms, which is finite. It doesn't grow with that. Okay, questions so far? Or that's fine. Okay, we'll have one more thing, and then we'll move to deterministic systems. So, so far we have ergodicity, mixing, entropy, K, and now we need to have Bernoulli. So there will be a difference between, so far what we've seen are Bernoulli shifts, and now I'll define Bernoulli systems, I think, and there's a big difference in this word. Okay, so let me tell you two more. To define Bernoulli, I need to tell you what a generating partition is. So a partition of the space is generating if any two different points have different names at some point. Okay, so I can separate any two different points by the atom. So I cannot have 2 points in my system that would fall into the same atom for all their life. Okay, so that's a notion. For example, this partition is generating for the classical Bernoulli shift because this means I see 0 on the 0th coordinate, this means I see 1. So if I start shifting it, right, I see any two points. If I take any two different points, they need to have a different letter at some point. So we'll see that. Okay, the partition is independent. So I have a finite partition. If here, okay, if you maybe it's the first time you see it, it looks kind of because there are these MIs, but this just is what I see for the coin toss. So seeing 0 on toss 1 and on toss 5 are independent. So this is what it means. So if I take an atom of the partition and I shift it by any numbers, then the measure is just the product. Okay, so for any for any atom, any two atoms become independent if I start shifting. So measure of the independence means measure of the product is product of measures. Okay, and T is a Bernoulli system, so not shift but system now. I think Ornstein used this terminology, so I will continue to use it. If there exists an independent generator. If you prefer measure theory, this means that as an abstract system, so I have an abstract system Tx mu, okay, it doesn't formally have anything to do with, X doesn't need to be, it might be the two torus or the circle, for example, but maybe it's abstractly isomorphic to the sigma on the space of, say, 0, 1, d, and some vector p and a probability vector. Okay, so this is equivalent. It's easy to see. I don't know which one is more. I mean, they are equivalent. Yeah, so Bernoulli shifts are K, and this is Sinai's theorem. So for Bernoulli shifts, any non-trivial entropy is positive, and this is an independent generator. So I mean, it's almost a tautology, but the Bernoulli shift is a Bernoulli system. What is interesting to study is the other direction. So you'll see in a moment that the theory was developed to what extent can a matrix on the two torus resemble a Bernoulli shift. So it's the other direction that's interesting. Okay, Kolmogorov actually conjectured initially that K and Bernoulli are equivalent, and this was shown false by Ornstein. So the fact that I have positive entropy for any partition doesn't mean I'm a Bernoulli system. I'm not isomorphic to a Bernoulli solution. And so far, here I've listed all the relations we've seen so far. So ergodicity is the weakest. It contains, sorry, is it the right way? Yeah. So yeah, ergodicity is the weakest. Bernoulli system, being a Bernoulli system, is the strongest. All the relations are strict. One thing I will not say much more. There is one problem that is central in the theory, not related so much to the talk, but I couldn't resist, is the rocking problem. So, you have this notion of mixing. So, 2 mixing means any 2 sets becomes independent. 3 mixing means any 3 sets. Any 3 tuple becomes independent, and this problem is surprisingly simple to state, and there is no answer to it so far. Okay, and now just two more properties. Everything we discussed so far is what you, I think, the way it was discovered is you study the shift that I told you, and these are the properties that it has. Two more that I'll just mention very briefly. You can talk about not only mixing, but you can talk about rates of mixing in your system. For rates, whenever you see rates, you need to have, you can't have it for any sets. So mixing, it's a L2, it's an abstract property. You can phrase it for any sets. Whereas if you want rate, exponential is kind of the optimal one you can see, the best one you can see. You need to somehow, restrict the family of sets you want to see it for. So, for example, if I take a Bernoulli shift, I take any two cylinders, this number is 0 if n is long enough, right? So seeing, as I said before, seeing something on a window from 0 to k, if I toss a coin, is independent from seeing it on the window from k plus 1. Okay. And the last thing that I want to define before we move to deterministic systems finally is the central limit theorem. Which means, so this, okay, it has a definition, but now if you do a coin toss n times, a symmetric coin, you expect to see half tails and half heads. That's just a Conic theorem or a strong law of large numbers, right? You want to see half of them, but there is an error, right? And central limit theorem tells you that the error is of order root n. So if I do it n times, typically I expect to see n plus minus root n of heads, and n, well, the other one is just the rest, but not more, for example, right? And it also tells you, I don't know if you've seen this central limit theorem, to what extent you, so it not only tells you what, that the error is usually of order root n, it also tells you that the error is distributed according to a Gaussian. That's the right hand side. So it's stronger than just saying that the error is of order root n. It tells you that, with what is the probability of seeing, for example, what is the probability of seeing, I toss it 1,000,000 times. No, I want to, yeah, I toss it n times. And what is the probability of seeing n over 2 plus root n heads? This theorem, well, slightly stronger version of it, tells you what is the probability of seeing this. Okay, or you can ask what is the probability of seeing n over 2 plus 2 root n. So these are the irregularities of distribution, right? And it tells you that the scale root n is the right one. So for example, you should not expect to see n plus n to 1/2 plus delta. So root n is the right scale, and it tells you that what is the error. Okay, so yeah, and this I said, again, the main example is Bernoulli shift. It satisfies these two. Any two cylinders become independent, and CLT also holds. I mean, this I won't discuss. There are various methods of proving this. So for IID, we have CLT. Okay, so hopefully I've defined some chaotic properties. Maybe you don't remember all of them, but maybe one or two is good. I mean, it's already fine, as you'll see later. So that's chaos, right? And now, this is the deterministic systems. Okay, so deterministic, the way we'll define it here is smooth. You can be slightly maybe more general, but I'll restrict to this setting. So now you see we had this abstract measure preserving system. And now what we want to have is this space to be nice, and this measure to be nice, and this map to be nice. And what do we mean by nice? Nice means, it's a compact, connected, reactable manifold. Maybe you can drop some of them, but I think just for this talk it's good to restrict. So you have a nice manifold, you have some smooth measure on it, so in local coordinates it's just volume, right? If it's d-dimensional manifold, it's volume, and then your map. Now we have a smooth manifold, you can talk about derivatives. So the smooth map, or you can do flow, like the continuous version, is now a map on M that preserves volume. Okay, so that's the setting, and the question now we are coming to the, I think, the main part, say, of the talk. We've seen all these statistical and ergodic properties before, entropy, Bernoulli, K, CLT, exponential mixing, and so on. And the question is, which of those can I observe here in this setting? Okay? And I'll give you two motivations for this, why to study this question. Probably there's more, but just a selective list. Somehow, you have natural examples. So, an abstract measure preserving system, quite often you construct it if you want some nice properties. And maybe then it's not very natural, but there were systems, for example, studied by Lorentz, the Lorentz attractor, where you see we have three differential equations with some parameters alpha, rho, and beta, sigma, rho, and beta. And this somehow was studied by Lorentz when he wanted to predict the weather. It turned out that this system of equations tells you, well, I'm not being quite vague, it models the change of weather. So if you would solve this with some precision, the better you can solve it, the better you can predict the weather. But in fact, reality showed you can't. His experiment showed you can't predict weather. This is the butterfly effect, where if you perturb the temperature a little bit, what he observed, I think, when you perturb the temperature or pressure, a little bit, which are the x, y, and z. Normally you have more. I think it's 10 quantities that you measure. Here there are just 3. But yeah, if you perturb the temperature a little bit, in 3 days the weather will evolve completely different. So small perturbation in the initial data leads to unpredictability in already a short term, like 3 or 4 days. So think of, just to relate, it seems to be related to entropy, where also perturbing means, I take a small, I take an x, I perturb it a bit, and I want to track it. So this should be the weather that I want to see, and this is the perturbation. And the more codes, if the codes are different, then this means, well, I already can predict.
So formally speaking, it is not in your class of systems.
It's contracted, yeah, it's volume, yeah. Maybe on the attractor, but yeah. And then there is Lorentz gas, which for some time, it's not a type. This was studied much earlier. And there's many more. I'm just listing. Then maybe you have just some simple systems. These are maybe the ones that appeal to people because you can just write them down and they are there. So for example, I take the 2-on-1 matrix. It acts on the plane. It is a transformation of the plane, but it is integer valued and therefore it descends to the torus. It has determinant 1, so it preserves area, right? And if you want, the leading question in this business of chaos, maybe of deterministic system is it's much more than that, but maybe what are the properties of this matrix? Initially, this was maybe not very known. If you maybe work a bit more in algebra, you can generalize this example. So this is it's an automorphism. But more generally, you can consider rotations or automorphism on the quotients of Lie groups. So this is a very simple Lie group, right? It's Lie manifold, where you take R2, a billion Lie group, but you can be more complicated. And then you have maybe systems from geometry, geodesics, flows, straight flows, and so on. So that's one motivation to study. The motivation to that was actually, to me, my initial background was in abstract ergodic theory, so this was somehow I was more drawn by this problem, which was a problem very open posed by von Neumann, and it is about having a smooth model. So I take an abstract system. Okay, so my space is a Cantor set, my measure is some nasty measure, and my transformation T is something. Can I find a smooth map on a manifold with volume such that these two systems are isomorphic as measure preserving systems, right? Notice that here the notion of isomorphism is really weak. You can't hope for better, right? So for example, you can't hope to have a continuous map from a counter set to a manifold. But the notion of being isomorphic as measure preserving systems is weak enough, or is, that this can happen. Okay? So just to give you an example, maybe you take a circular rotation, R alpha, on this one, right? It preserves one-dimensional Lebesgue measure, and let alpha be the golden mean. Okay, and this is already a smooth system, so it kind of doesn't fall into this setting. But you can ask, is there something isomorphic to this on the disk? So now I take the two-dimensional disk, and I take dphi of f of the disk that would preserve area of the disk and be isomorphic to this one. Okay, here there's boundary, here there's not. Right? So it's kind of a, von Neumann asks about this system being abstract, but as I said, abstract systems are not so easy to define. They're usually constructed, which means I can give you a simple example of this. But already the problem of realizing a one-dimensional rotation on the two-dimensional disk is open. If this is Euclidean, you can do it, but generally it's open. And many other simple abstract systems, like if you know what the odometer is, the ending machine, just the two odometer, we don't know if it has a smooth model, so if there is a smooth map that behaves like the odometer. Yeah, this is the motivation case. It's Sinai's wrote a survey in which he said, and we'll see later, he said does there exist a system which, for example, is exponentially mixing but does not satisfy CME? So what is the dependence and independence of these properties that I mentioned? And just to tell you, this is one of the nice conjectures in the field in 1952, I believe. So you see, every smooth system has zero entropy. This was conjectured by Kolmogorov. So in particular, let me go back. This matrix, right? It is a smooth system. It should have zero entropy. As we'll see, it is very far from true. So, for example, this matrix here, it has positive entropy. It's log of the larger eigenvalue. Okay, but yeah. So,
but Arnold was a student. He gave that example.
Arnold, okay.
He gave that example.
Of a smooth map with positive entropy.
2, 1, 1, 1.
Okay, the cat map. Yeah.
It was probably a question like, give an example of a smooth system with positive.
Right.
Do you think it was conjecture?
No.
I saw it.
Sounds very strange.
No, I saw it.
His student gave that example.
I found it in one. I can show. I mean, it's written in one of his proceedings. That with all probability, all systems of something like this. I mean, it's in. Oh gosh.
I'd like to see it.
Okay. Okay.
Maybe it was the second day at my interview.
I think it was before. I don't know how much. Yeah. I can show you that. Yeah. Okay. But yeah. Okay. Now it's clear. It's not.
Maybe it's a probabilistic.
Yeah. Then we enter different. Yeah. Then we enter different. Well, he said with all probability. I think. Yeah. Okay. Now this turned out to be wrong. Okay, but there is something that is true. So every system has finite entropy. So if I take a smooth system, I can't have infinite entropy. There are abstract systems with infinite entropy. They're easy to construct, basically Bernoulli of infinity many symbols where the phase space is n to the z. So natural numbers to the z. But smooth system has finite entropy, and the idea, back then it was considered, but the idea behind this is that the orbit separation is controlled by the derivative, right? So if I take 2 points, if you view entropy, which is somehow a useful viewpoint, is I take a point, how much can I perturb it so that they still see the same future for n steps? So here it's clear that if I have a C1 map, at least I take the derivative, right? It will be controlled by the growth of the derivative at the first n steps. So if I perturb it less than the derivative cocycle, than the derivative of the first n steps, then this point tracks this point. I mean, I can predict the future of this point by this point, and therefore I have finite entropy.
Do isomorphic systems or isomorphic instances that you mean have the same entropy?
Correct. Well, yeah, sorry, I should have,
So then I'm confused because if smooth systems have finite entropy, and you gave an example of an abstract system with infinite entropy, then what does that say about the smooth realization problem?
So, exactly. Very good catch. So, you can realize systems of infinite entropy, but this is since the work of Kushner entropy only obstruction. So, yeah, there is something. That's the result. It tells you can't realize infinite entropy systems, but somehow, that's the only one we have. Good catch again. All the ergodic properties are invariant under measure theoretic isomorphism. So that's maybe I should say. That's why it's useful to study ergodic properties. And it's exactly by the principle, right? So here you say smooth system has finite entropy. I construct an abstract system with infinite entropy. It is a measure theoretic invariant, and therefore I can realize. So one reason, at least the motivation coming from working on the von Neumann problem to study this is maybe in smooth setting, for example, let me just try to shoot at something. Bernoulli and K are equivalent, which is not true. So K, Kolmogorov property, and Bernoulli are equivalent. Now we know in abstract it's not. So then if you could find, right, so the way you study this von Neumann question is you try to find some rigidity in the class of smooth systems. Like one approach, not very successful. So that's that. Just to tell you how little we knew in the beginning, so you take the disk, and it was not known if we can find an area preserving ergodic field of the disk, right? One simple map of the disk that we had is just you rotate on circles, right, like this, but clearly it is not ergodic because any circle is invariant, so I have plenty of invariant sets. But then Anosov and Kakov came up with the construction of an ergodic diffeomorphism of the disk. It's what's called the ABC method now. And in fact, you can, 10 years later, a different construction by Kakov, Feldman, and Rudolph showed that you can do Bernoulli. So every manifold supports a Bernoulli system.
Word manifold means compact manifold.
Compact manifold.
With possibly with boundary.
Probably they do with boundary as well. Yeah.
But it's the last one with include with boundary.
Let me think what they. Okay, their paper is no boundary. Now the question is if we can extend it to, if the methods work, I would have to think. Sorry, you had that question.
No, but I'm just saying that does their theorem apply to this or not?
So dimension larger equal than 2, yeah, it applies to the disk. But it's a different construction, very different from this. Basically, it comes from the slowdown of the 2-1-1 map. It's a theory of non-uniformly hyperbolic systems. Now this may be slide I'll skip because I told you about this motivation to study them, and this is just one slide that I wanted to put here, but I won't talk too much about this. The reason, the main success of the theory was the hyperbolic systems, and people studied. There is a notion of so if I have a smooth system, I can define the notion of hyperbolicity, and there is a lot of success in studying this. Maybe I'll just give you one example because I'm not sure. If you work somehow close to dynamical systems, this is going to be clear. What I say would be clear. If you haven't seen it, it's probably too difficult to say, so I'll just give you one example of a hyperbolic system. And this is exactly the 2-1-1 map. It's called the Arnold's cat map. And what it does is acts on the torus, and here you see some few iterates of it, right? So you see I start with a triangle. One thing to notice is I start with a triangle, so a nice shape, and after already 2 iterates, you see the triangle seems to be quite chaotic. I mean, it is cut into many pieces, and actually all the triangles are like this. And this is a baby example of a hyperbolic DFU. And here I'm trying to define it, what hyperbolic means, just in this simple setting. So if I take any point in the plane, in the torus, it turns out that the tangent plane of the torus, which here is just R2, splits into 2 directions, EU and ES. One is contracted by the derivative, and the other one is expanded by the derivative. So here it is very simple to see what the EU and the ES are. So this matrix 2, 1, 1, 1, you can do a direct computation and see it has 2 eigenvalues, lambda, lambda inverse, one bigger than 1, the other one smaller than 1, and it has 2 real eigenvectors, V1 and V2, and one of the eigenvectors corresponding to the eigenvalue bigger than 1 is extended, and the other one is contracted by the Okay, so that's somehow what happens. Okay, let's see how much time we have. Maybe I'll one of the success I wanted to mention is how do we study these systems, hyperbolic systems? We study them through Markov partitions. So as I said here, one of them, from the ergodic point of view, the important theorem here is Bowen and Sinai, independently, I think, about Markov partitions. So whenever you have a hyperbolic system, it turns out you can associate with a certain Markov partition. And I just wanted to give it of this example, a very simple one, an example of a Markov partition, and maybe this will show you why it might be useful. So we take just the circle doubling map, we take a partition of the circle into 2 equal halves, and we code any point by a sequence, again, as we did here. It's the same thing. And you can always do that. The interesting thing and the important thing is that the coding is uniquely defined for almost every point, and it turns out that for all but countably, essentially all but rational points, the system is conjugated to the full shift of 0, 1 to the n. So if you give me any sequence of 0 at once, I can associate a point on the circle such that the dynamics of the doubling map is just the shift of 0. So think of a point taking the binary expansion. What the shift does to the binary expansion is what 2x mod 1 does to the binary expansion is it eats the first coordinate. Right? So 2x mod 1 on the binary expansion acts as a shift on here is one side shift on 0, 1 to the step here. And there are exceptions because, for example, 1/2 has 2 codes. Right? But, yeah. So
Not conjugated to the full shift, it's one-sided shift.
here it's one-sided because the map is not invertible, right? 2x mod 1, yeah. So that's the simplest example of a Markov partition that I could think of because you're conjugated to the full shift. The problem with the map is it's not invertible. But you know, that's 2x mod 1, and therefore it's going to be a shift just one-sided. But it turns out that this map, for example, also has a Markov partition. So what you do is you take a torus, you split it into certain rectangles, not these ones, but I think 3 rectangles would do, and you code now the same way as here.
You mean triangles?
So, I think they are parallelograms.
Okay.
Yeah, you can divide each part. Yeah, it's not unique. A Markov partition, you can. There is a you can pick your favorite one. I think the one usually people use are 3 parallelograms. And it turns out that if you do that for the 2, 1, 1, 1 map, and you just code every point, you won't get the full shift. Now it's invertible, so your ideal situation would be if you got the full shift, but you don't get it, and that's why I decided to give you this map. Because here you really get a full shift, so it's simple. For the case of 2, 1, 1, 1, you get something that's called subshift of finite type. So you get the subset of all sequences where you can't see 2 consecutive zeros. It's called the substrate of finite type. So basically here you can't, what this translates to is you can't be twice in one atom the way you construct the atoms. But it's, it's good enough, and the idea is, I want to study this map, or say the 2 1 1 1, I conjugate it to this one, and this one, it's a shift, so all the properties that I wanted, I discussed before, they work here, which means they also work here. The problem with hyperbolicity is that it is a rare thing. For example, it is conjectured that hyperbolic systems roughly live only on tori, or infra-middle manifolds. But most manifolds likely don't support any hyperbolic system. And then, the theory of partial hyperbolic systems was developed.
I think I once wrote a paper proving there's C0 tens in any manifold.
No, but okay. By hyperbolic, you mean and also you mean there is a hyperbolic set.
They're not areas.
Okay. So no. So here by this I mean what people usually I call them hyperbolic, but probably people call them Anosov systems. So what do I mean by that? It's a volume preserving map such that every point on the manifold has a split.
This is most important. Since people often call hyperbolic just axiom A.
Yeah, I know. Yeah. Here I didn't define what they are. So sorry, sorry for that. But for here I mean everything is volume preserving or smooth measure preserving. Yeah, if you allow for contraction, like the Lorentz, or then the picture is completely different. So here, what is important is that first of all you have the splitting of the whole space, and second, somehow the eigenvalue the area is preserved, so you can't contract it. Okay. So let me tell you now, maybe the last 10 minutes, I think, or 5 minutes. Yeah, 5 minutes, I'll just list some results. I will recall what I defined before. K property means that every non-trivial partition has positive entropy. Bernoulli property or Bernoulli systems are those that are isomorphic to Bernoulli shift. So again, this was another I can show if needed. The conjecture of Kolmogorov that K and Bernoulli are equivalent. I think his idea to introduce K, as far as this now is, I just spoke with some people, is that he wanted to classify Bernoulli shifts, and the K property was more accessible somehow. Okay, here, so K and Bernoulli are not equivalent. So here, in fact, in smooth, in dimension 2, so everything is always measure preserving. That's what I always assume. Here, technically, there's another abstraction to smooth realization, if you want. So K implies Bernoulli in dimension 2, that's a result of Bessin. And therefore, you take this system that is K not Bernoulli, and you can't realize it on the surface. That's another abstraction, but also quite fun. And then the question was to what extent K and Bernoulli are equivalent. So in dimension 2 they are. Katok constructed an 8-dimensional example where they are not. Rudolph gave a 5-dimensional one. We gave a 4-dimensional one. 3-dimensional one is very open. I think, Katok phrased it 3 open because at that time Rudolph was the best. He was.
These are all values.
Yeah, everything is area preserved. I think Katok said 3 or 4, but so now that the 3 is really open, this is kind of a big, no tools here.
So it's true in 2,
Not true in 4.
true, and not true in 4 and above. 3 is open.
3 is open, and very difficult.
That's good.
Is it 4 and above or just 8, 5, and 4 we know?
No, I think you can construct examples in any dimension above 4, including 4.
Fluid.
yeah, it's really the dimension is really the 3 is critical. It's not that all tools that we have in dimension 4. I mean the tools that we use in these higher dimensions they completely break down in dimension 3. Just okay, I can call.
What is K meaning?
K over every partition has positive entropy.
What?
Every partition has positive entropy. Yeah. And Bernoulli means okay, maybe one last thing I want to say. So now when I move to kind of smoothly without, so now you want to know to what extent smooth systems can, what's the zoo of statistical properties in smooth systems. So for example, this tells you that K and Bernoulli, which initially were maybe thought to be a counterexample, they really can't. Still maybe in dimension 3 they are. And one last thing I want to say maybe is a relation between exponential mixing and entropy. Okay? So exponential mixing of entropy, exponential mixing was long studied in smooth dynamical systems through transfer operator, for example. And I just recall the definition. The system is exponentially mixing if correlations. So I look at, I take 2 observables side to side, I subtract their means, I iterate them times, and it should decay exponentially with some exponent kappa. Here it's equivalent. You can talk about observables or you can talk about balls in the space, which was what we did before. And one question that Katok asked was, does exponential mixing imply positive entropy? And we have shown this not so long ago.
The mu in that theorem is true.
It should be volume, yeah. It should be volume.
It should be a volume.
Yeah, sorry. It is, yeah. Here mu and here mu is a smooth measure of the manifold. So the last maybe theorem I want to talk about is that if we take a diffeomorphism that is exponentially mixing, then it is isomorphic to a Bernoulli shift. And since it's isomorphic to a Bernoulli shift, it has positive entropy. It is interesting that this property, so this is maybe the last thing I want to say, and this is where we want to study, but we don't have, it seems apparently, so, our result shows that exponential mixing shows Bernoulli, but we really use smoothness. We use, first of all, that the measure is smooth, that I have a manifold, and that I can use Hessian theory, basically. The output of exponents and so on. What is not known, and this would be an interesting example, so this maybe I'll finish with. So you take the shift on all infinite sequences, and here I put some measure theta. Let's call it mu. But it's not the Bernoulli measure, right? So I have a space 0 up to the z, I have the shift, and here there's plenty of measures I can put. Like shift. The number of measures that the shift preserves is enormous. And I do the measure mu that satisfies that for any 2 balls, v1, v2, measure of, sorry, it should be mu of sigma n v1, intersection v2. Basically, I want to write exponential mixing for this measure. mu v1, v2 is less than e to the constant, e to the minus kappa n. Okay, so it's the same definition as here for balls, except in the symbolic setting, but it perfectly makes sense. Right, so in other words, I take the shift with an exponentially mixing measure. Does it have positive entropy? Why is this interesting? If you look at this theorem 1, and the answer to this would be no, then this thing here with some extra work, but I think the extra work we've already done. We can do this. This would be a counterexample to the smooth realization. So you see there is a property of smooth system, which is exponential mixing, that gives you some rigidity, which means I have positive entropy. In fact, I'm K, I'm Bernoulli. And here it seems that, I mean, we can't really get that, but we have intuition showing that it shouldn't be the case for symbolic systems, for exponential mixing measures. And this, then, I mean, this system then would be potential, I mean, good candidate system. so I think I'll stop here. Thank you.
Any further questions?
So here do we use an time state? So do we use a state machinery for this last theorem?
The first step is to show that if I'm exponentially mixing, then I have a positive exponent. Once I have a positive exponent, I have unstable manifolds. And then exponential mixing implies an exponential distribution of those manifolds.
So you don't exploit time states machinery more directly construct the Bernoulli.
Yeah,
The
yeah.
Bernoulli generator.
Yeah, sorry, no, exactly, sorry, I understood your question. Yeah, so, Ornstein, we use very good, you can't access, I don't know of any single smooth system where you would find an independent generator, right? That's why it's so difficult. That's why I think Ornstein's theory is so powerful.
It still stays strong.
Yeah. Because most likely, the independent generator is going to be a nasty partition, right? It's not going to be a smooth one. So,
And so what is the central problem with this kind of set of ideas now from your point of view?
well, there is quite plenty, I think. For example, it is not known if exponentially mixing of order 2 implies exponentially mixing of order 3. That's one. It is not known if exponential mixing implies central limit theorem. That's 2. It is not known if an exponentially, just with each of these properties, you can more or less ask these questions.
And you just put a general vegetarian state, smooth state.
Smooth setting. So, another question: is it true that any 3-dimensional, 4-dimensional manifold supports an exponential mixing system? This is not true. Does every manifold have an idiomorphism, area preserving, that satisfies a COD? That's not. So is there another one that I'm working on? I can list, but these are. I think my favorite one recently is there is an example of Katz-Nelson of an abstract system that is uniquely ergodic and has positive entropy. Uniquely ergodic and positive entropy, right? Shift has many parameters. He shows one that has only one. Michel Herman constructed a diffeomorphism that is minimal and has positive entropy. But we don't know if there is something that's uniquely ergodic and positive entropy in this whole set.
That theorem is an assumed use volume.
Yeah, it uses smoothness of the measure. Yeah.
But any manifold, smooth manifold.
Here it's any smooth manifold. Yeah, compact, finite dimension. Yeah, compact manifold. C1 plus. We need C1 plus something. C1 plus.
So the Tata question is true in the smooth context.
Correct. We don't know. Yeah, exactly. We don't know if it's true in this abstract.
What if you look at special manifolds, Tauri groups that have one structure where you have a Fourier transform? Does it help you?
It helps. So, for example, there was a question. I didn't have time. I have it on my slides, but I think I will. Okay. There was a question whether central limit theorem implies positive entropy, and we can show an example for which it's not. So there is it's kind of a surprising, I would say, exotic, like a strange diffeomorphism of the 4 torus that satisfies central limit theorem, but has 0 entropy. So, for example, here we use a lot of Fourier harmonics. Yeah, it's on my slides later.
What's the question about 3-manifold?
Thus, the K property. So K property means every partition has positive entropy, imply that the system is isomorphic to Bernoulli shift. We know in dimension 4 it's not. We know in dimension 2 it's yes. And in dimension 3 it's very.
What does that do? Just
Exponential here it's not K. Yeah. K is much weaker. This somehow it's also surprising. Exponential mixing implies mixing of all orders, for example. This is another consequence of this, which is right because Bernoulli are mixing of all orders, so this relation is wrong with the problem. But yeah, K on Bernoulli is open in dimension 3, and I think we open. And actually, sorry, you asked about the Lie group, so I think I first proved this for D groups, as you say, using some extra structure, and then we are able to get it, get some business. Okay. Thank you very much.